In the infinite theater of the cosmos, where light takes millions of years to traverse the emptiness between stars, a silent wanderer traverses the void, the Atlas comet. At first glance, it appears as a typical visitor from the outer reaches of our solar system, a frozen remnant of cosmic history made of ice, rock, and dust. But beneath this familiar exterior lies a secret that threatens to rewrite our understanding of the universe itself. For centuries, humanity has looked up at the night sky and traced the paths of comets, marveling at their tails of glowing gas and dust, marking their fleeting journeys around the sun. These icy travelers have been regarded as harbingers of change and mystery, celestial time capsules preserving the earliest materials from the solar system's formation. Yet the Atlas comet reveals that even among these ancient bodies, there are wonders yet undiscovered, wonders that challenge the very laws of physics. The comet's orbit does not conform to established gravitational models. Instead, it twists and shifts, its trajectory subtly but unmistakably altered by forces no one fully understands. Around it, space-time itself seems to ripple unpredictably, hinting at an unseen presence whose influence extends beyond the visible. This presence, dark matter, has long eluded direct detection. It neither emits nor absorbs light, remaining hidden in the cosmic shadows. Yet its gravitational pull sculpts the motion of galaxies, the formation of large-scale structure, and now, as we have learned, even the path of a comet. Until the discovery of Atlas, dark matter was believed to exist only as a diffuse, almost ghostly halo around galaxies, a cosmic glue invisible to our eyes but essential to the architecture of the universe. But the Atlas comet carries within it a concentrated pocket of dark matter, bound intimately to its icy nucleus. This unprecedented finding overturns previous assumptions and opens a new window into the hidden cosmos. Gravity, the force that pulls us to the Earth, binds planets in their orbits, and holds galaxies together, has been studied since ancient times. Newton's laws described gravity as a force acting at a distance, pulling masses toward each other with a strength proportional to their mass, and inversely proportional to the square of the distance between them. For centuries, this elegant description explained the orbits of planets and the tides of oceans with remarkable accuracy. Einstein's general relativity refined our understanding by revealing that gravity is not a force in the traditional sense, but the curvature of space-time caused by mass and energy. Massive objects bend the fabric of space-time around them, causing smaller objects to follow curved paths, what we perceive as gravitational attraction. Yet the gravitational behavior observed in Atlas does not fully align with either Newtonian or Einsteinian predictions. The comet's path exhibits fluctuations, subtle accelerations, and decelerations that suggest space-time around it is warped in complex ways. These anomalies imply the presence of a gravitational field influenced not only by visible matter, but also by an unseen mass concentrated within the comet. This realization forces us to confront the limitations of our current models. What if dark matter is not merely a passive background presence? What if it can cluster, bind, and interact gravitationally with ordinary matter on much smaller scales than we ever imagined? Dark matter is the silent architect of the cosmos. It makes up roughly 85% of all matter in the universe, yet its nature remains one of the greatest mysteries in physics. It neither reflects nor emits light, making it invisible to telescopes. Its existence is inferred solely from its gravitational effects. The way it influences the motion of stars and galaxies, bends light traveling through space, and shapes the cosmic web of galaxy clusters stretching across billions of light years. Until the Atlas comet, dark matter was thought to form vast, diffuse halos that surrounded galaxies, extending far beyond the reach of visible stars. These halos create the gravitational pull necessary to keep galaxies from flying apart despite their rapid rotation. But the dense dark matter core within Atlas challenges this picture. How did this dark matter clump form? What keeps it bound to the comet's nucleus? Could dark matter particles experience forces beyond gravity? Forces that allow them to form compact structures? These questions cut to the heart of particle physics and cosmology. In the quest to identify dark matter's building blocks, physicists have proposed numerous candidates. WIMPs, weakly interacting massive particles, are hypothetical particles that interact primarily through gravity and the weak nuclear force, making them difficult to detect. Axions, sterile neutrinos, and other exotic particles have been theorized, each with unique properties and detection challenges. The Atlas comet may contain a concentrated dark matter clump composed of these particles. If so, it provides a natural laboratory for studying dark matter in unprecedented detail. Instruments aboard space probes like Odin, 9, and Horizon were equipped to detect subtle gravitational effects, particle interactions, and electromagnetic signatures emitted indirectly by dark matter. Data returned from these probes reveals a complex picture: gravitational fluctuations interwoven with faint signals resembling mathematical patterns, prime number sequences, the Fibonacci spiral, and constants such as pi. These patterns suggest that dark matter may encode information, perhaps hinting at a cosmic language or intelligence embedded in the universe's fundamental fabric. The discovery of mathematical sequences encoded in dark matter raises profound philosophical and scientific questions. Is the universe fundamentally a mathematical structure? Could these signals represent natural patterns emerging from physical laws, or are they messages from an intelligence beyond human comprehension? Some scientists speculate that dark matter forms a cosmic information network, a vast quantum computer running the universe's operating system. Others ponder the possibility that the encoded patterns are the remnants of a primordial intelligence, echoes from the dawn of time embedded in the quantum substrate of reality. Such ideas challenge our conceptions of life, consciousness, and communication. They push the boundaries between physics and metaphysics, urging us to expand our definitions of intelligence and existence. As Atlas approaches the inner solar system, its gravitational effects are not confined to deep space. Subtle perturbations ripple through Earth's magnetosphere, altering magnetic fields that govern everything from satellite operations to animal navigation. Biologists observe shifts in migratory patterns and behaviors in birds, whales, and other species that rely on geomagnetic cues. Even human physiology shows faint signs of influence, variations in sleep cycles, mood fluctuations, and cognitive effects recorded by neuroscience studies. These terrestrial responses highlight the interconnectedness of Earth and the cosmos. Our planet, though seemingly isolated, is part of a vast system of forces and influences reaching across light years. The approach of Atlas has galvanized humanity like few cosmic events before. Nations set aside rivalries to collaborate on observation, data analysis, and mission planning. Global observatories work in concert, sharing data in real time. Citizen scientists contribute observations, while artists, poets, and philosophers interpret the comet's mysteries in cultural expression. Schools incorporate lessons about dark matter and cosmic physics, inspiring a new generation of explorers. The event rekindles humanity's sense of wonder, reminding us that we are part of an ever-expanding story written among the stars. Yet with discovery comes responsibility. The risks of engaging with an unknown dark matter anomaly are real. What if probing Atlas destabilizes its core or alters gravitational fields affecting Earth? What if the encoded signals are a form of intelligence that requires respect and caution? Scientists, ethicists, and leaders debate guidelines for cosmic interaction, giving rise to a new field of cosmic ethics. This framework balances curiosity with humility, scientific inquiry with caution, and recognizes our duty to preserve cosmic harmony.